Okay, so today is the last of my series of 6, and let's much more rapidly go through the story. So we are setting up this cohomology theory or homology theory, whatever. It has maps in both directions. This homology and cohomology, these names are usually related to whether there is push forward or pull back. This thing is going to have appropriate kind of both, so homology, cohomology, whatever. It's for algebraic schemes over a base field, and you know how they look. You can draw a picture of an algebraic scheme. It has lots of irreducible components, but finitely many. Each one is a variety, but each one is sitting there in that scheme with some amount of thickness going about, and that thickness can be measured as the length of the Artin local ring at its generic point. But there is also some extra thickness here and there, some close subvariety with some extra stuff, and that the more precise algebraic notion being associated primes. When you are doing things in an affine open, when you are talking about schemes, what are associated primes called? Perhaps they are called associated points, because primes become points. Okay, but I don't remember seeing such words prominently. Associated points. Yeah, Chetan, Anand. Embedded points is perhaps it is called. No, embedded components is the word I have read again. But yes, you are right, embedded, because those are called embedded primes. The ones which are not isolated are called embedded. But they might after all be minimal also. I like to call minimal primes also as associated primes. Then I won't be able to call them embedded. Anyway, there may be some name, those things. So you can visualize algebraic schemes, and you understand the importance geometrically of the local ring somewhere. You want to study in the neighborhood of that point, so you go to the localization there. And then, being a homology theory, I first want to know what are cycles. Those are very closely linked to geometry. They are generated by the irreducible, reduced, closed subschemes, the closed subvarieties, which need not be separated. And so I should ask you, now that you have looked at lots of Chow groups, and all of you know this affine line with doubled origin, yeah? Figure out the Chow groups of that. Second exercise. Take projective line with doubled origin, or doubled point at infinity, whichever way, and find out its Chow groups. And because we have allowed ourselves to count Chow groups with non-separated varieties, you will get a nice answer, it will behave nicely. Imagine for the moment with these examples that you had insisted that to count to make Chow group cycles, you need only separated varieties, the Hartshorne definition of variety. Then see what will happen to these two examples and how things are not that well behaved. Okay? So with these two very simple examples, doubled origin affine line or doubled point at infinity projective line, you can convince yourself that one indeed needs non-separated varieties in order to have good theory. Yeah? So do it. It's all do-it-yourself stuff. So now some technicalities, close varieties in terms of their generic point, their transcendence degree of their extension is their dimension. So the points of an algebraic scheme get partitioned into points with different transcendence degree, etc., all that you know. And then came the idea of defining equivalence between cycles. There are far too many cycles, and you want to systematically forget unimportant differences. You want to focus on what is important, then you want to identify. Like take something very simple. You are sitting in this chair? Yes, you are. Now also you are sitting in this chair, he moved his legs. Oh, he adjusted himself. You are sitting in this chair? All answers are he is sitting in this chair, because those other things are unimportant. Yeah? If you actually look at where each one of his atoms is and what is its momentum, they are completely different positions. But the way we understand for our practical purposes that I have to sit in this lecture, all those have to be identified. Because remembering all those differences is completely useless. Okay? So you have to club together a whole lot of infinite data to arrive at some finitely many few answers. And you know, in singular homology, the number of cycles, dimension of that, uncountable. But finally, the singular homology is some nice finite So immediately you should ask, we have kept mum on this subject. I don't want to keep mum on things. Just because I won't answer those questions doesn't mean I won't ask them. So you might ask that I have predictive varieties, I have the chow groups. Are they finitely generated? There are far too many cycles, but after going modulo, is the answer finitely generated? Answer is no. So again, do it yourself project. Now that you know what are chow groups of various things, even with curves you can see 0th chow group of a complete curve. Is it finitely generated? Yeah, you should be able to answer this now. Okay, but anyway, the point is we have to club together a whole lot of cycles to keep what is essential and leave out what is inessential. And we chose rational equivalence for that. And this choice we'll justify at the end of today's lecture. And after doing that, we club together cycles. So for that, we need the technicality of what is the Weyl divisor of a rational function. That is what we are going to say is 0. And to know this Weyl divisor, I need subvarieties of one dimension less and how much the rational function vanishes or how much it has poles there. So I need a mechanism for counting zeros and poles. The technical part of the narrative, and that we did with length. Okay, and that's where all your knowledge of art in rings from your Atiyah McDonald chapter is deployed to understand how all this works. And so this is over, and we went modulo that and got the chow group. And then we checked what it looked, what was it beyond dimension, what is it below this, what is it for fine line, what's for fine space, blah, 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 blah. I was going to do some of it, but some of it has been half done for you already in yesterday's lectures. And then we started making it after setting up the groups. Now we are interested in its functorial behavior. What happens under morphism? What happens under what kind of morphism? Can I push forward? Can I pull back? At the very least, is it functorial with respect to isomorphisms, automorphisms? And that it was, very least, but something more. So we set up proper push forward on cycles. So the push forward has a geometric meaning. You understand what geometry you can do with this pushing forward because this cycle is going there. And then when you have gone modulo all this, for it to happen at the chow group level, you have to say that the equivalence is preserved by this push forward, and which we verified it is, and that was a long verification spilling into 2.5 lectures. And that is called whose theorem? Called meaning I call it. Whose theorem is it? Chevally's theorem, Chevally 1945. Chevally in 1945 gave the first modern treatment of intersection theory in a seminar in Paris. And perhaps it's part of, I don't know, maybe it was just Seminar Chevally. After all, there was a long seminar running called Seminar Chevally. And one of the great things which, and I'm telling you stories, and please remember, the stories are also part of my lectures. Otherwise, what's the difference between a book with everything in the type of the same thickness? And you're reading it, everything the same. But there is a theme, and there are some important things, and there are some less important things, and there are some milestones, and there are some landmarks, and you need to be shown those things by a living mathematician. And so that's why there are these schools instead of you're just reading. That's why teachers are important. Teachers can't help you go through a page of technical argument, a page long, that you have to do yourself. But to know the story, that's very important. We are not machines. Okay, so you have to know such history, that at the midway through the last century, the French really organized themselves under the leadership of André Weyl and a group called themselves Bourbaki. They said that mathematics has to be redone rigorously in the light of new discoveries and written down. And so all kinds of new discoveries were not only presented, but they were written down. And the audience were young people of your age who were given the job that you write down all this, and the general idea is this, but you fill in the details. So they developed technical ability, and they were with the story as it developed. And that set of young people became the next real greats of mathematics. So people like Grothendieck, Serre, X, Y, Z were part of all this from very young age, and they were very quickly given the jobs of writing. Grothendieck had a large number of young men and a few women also around him, and who were given jobs of writing. And that produced people like Verdier, Serre, Reynaud, Illuzy, all the big names you hear came out of this, being told to write this. Chevalier was one of the leaders of this. He was already a very great mathematician. And he ran a seminar, and all the seminars were named after the mathematician in charge of it. So there was Seminar Cartan, Seminar Chevalier, various other seminars were running. And people gave talks in it. The insistence was notes have to be given. You cannot just go and give a talk. You have to give notes. So all people who gave talks gave notes. And those notes became the basic text from which the rest of the world started learning mathematics. Of course, everybody had to learn French for that. And with a 3-month delay, the notes of Seminar Cartan started arriving in TIFR, where there was a bunch of graduate students in their second year. And with nothing, there was no mathematics in India of the advanced kind. There was this great man and his stuff, but that's not to everybody's taste or ability. So there are these unemployed young guys very keen to do mathematics and no mathematics. And then as the things would come by mail to TIFR library with a few months delay, these guys would pounce on it and run their seminar in TIFR. And of course with a French dictionary in one hand. And they went through Seminar Cartan and all such things as they came and taught themselves modern mathematics. So modern mathematics came to India because this set of young people really worked their ... off, and half the night they're running their seminars. So, for long years in TIFR, there was this phrase called night seminar. All of us ran these night seminars, which went to 2 a.m. often. So, you guys have to, you are in some sense very fortunate because you already have in front of you teachers who have some knowledge of world mathematics, history, advanced technology, and somehow many things are being given to you in a, but there is this self-reliance, which is very important, where you can, and that is where teamwork is important. No one kid in TIFR could have done it. They were together. You read this, I'll read this, I'll hack through this. It's like going to Everest for the first few people where there was no great technology. And they would take turns digging the steps, and then you'll be tired. Then the other guy will take the lead. Okay? Even in a bicycle race, Tour de France, you see how the bicyclists, the top ones in the world, how they go? They are in a line. Why? Because then the second one, third one has less air resistance. The front guy takes the brunt of the air resistance, and they all go closely behind it. Then at some point, he is tired. They are all considerate on that point. He falls back. And then the second guy takes the brunt. You will see it happening in that top race for top money, that cyclists taking turn to lead and getting tired, and they go back. And then they come within, say, 2-3 kilometers of the end, you are on your own because you have to decide the winner. Yeah? So teamwork is extremely important. So that's why I'm telling you guys that learn to cooperate, learn to run a night seminar together or a day seminar for that matter. Share what you know with others. If you have learned something interesting, go and say, I learned this today with great excitement. That is what makes the atmosphere of a mathematical place. Not each one for himself. Okay? All right. So Chevalier devoted a year or perhaps 2 years, I don't know, 1 year, 2 volumes of the seminar, to narrating intersection theory in its modern form, because the Italians already had intersection theory with huge, let's say, gaps, but great intuition. So while modern algebra was being developed, quantitative algebra was being developed, and algebraic geometry was getting phrased in terms of all these new techniques, somebody had to take the lead and start putting intersection theory in this form. So Chevalier ran a seminar on intersection theory. That is the origin of modern intersection theory. Chevalier did this for many other things. Chevalier set up the modern theory of algebraic groups, for example. And Grothendieck, in many ways, is a follower of Chevalier. And who started using schemes? Chevalier. Nagata, these people had the ideas which led to the final definition of schemes that you have now, which was earlier called pre-schemes in EGA, but later the name changed to schemes. Anyway, schemes were separated pre-schemes. So Chevalier has done a great contribution. Have you read his book, Theory of Lie Groups 1? Take a look. Very interesting. Chevalier defined manifolds in terms of sheaves in that thing for the first time. Okay. So we did Chevalier's theorem, And this was a digression on telling you this push forward wheel device is Shirley's theorem. With that go the story. Story is as much part of proving the theory. So all this is the technicalities of pushing forward wheel divisor and how it works, which we have gone through a number of times. So I'll fast forward to the technicalities. And then comes the idea of pulling back. There one needs flatness. And then you have to ask yourself, hey, where did we use flatness? Let me look at the whole proof and mark in red all those spots where flatness was important. Let me also mark all those spots where relative dimension constant was used. Let me see by tweaking the condition how much I can push through without this. Let me try an example of a non-flat map and see what happens and so on. And you'll see all that stuff is needed in these constructions. However, in actual mathematics, you need all kinds of maps which are not flat. And you want to pull back, you want to restrict attention somewhere. He's pulling back. And the prototype of a non-flat map is a proper closed inclusion. Okay? A mod I in general, sometimes A may be split into direct factors and I might be defining one of those factors. Then it is flat. But otherwise A mod I is not flat. Why? Because the I inclusion into A when you tensor with A mod I becomes 0. The map becomes 0. Okay? So earlier it was inclusion. So A mod I means a closed subscheme, closed subvariety, whatever. That is not flat. But often you have something happening in projective space, that's your ambient thing, but you are sitting on a hypersurface or a smaller variety and you want to restrict stuff there, that is pullback. So you are going to need non-flat pullback very badly. And that is difficult. Okay? All the flat pullback we set up was for flat and constant relative dimension. But what you really want also, well, there are enough examples of that also, bundles, whatnot. The ambient things are going to come like that. But the specific thing inside, no. So you want to be able to restrict things there. That is the effort going on in the lectures of Chetan. He is showing you how to restrict to something which is something proper closed inside instead of a flat pullback. Okay, that's much more difficult. And how to do it? Somehow bring it to a situation where things look somewhat better, deformation to normal cone, etc., etc. Okay? So, but to really digest all that, you need this as first step. So how did we handle flat pullbacks? I gave you my straight walk ahead of the nose proof. Only thing it needed, which is not there in Hartshorne and standard basic things, was the notion of meromorphic functions on schemes and their pullbacks and their divisors. But that is simple technology, and simple technology of this kind known to experts and not written. Okay? So I have written it, and that's there in your notes and in that archive paper that I told you. So read it there, but make it part of. So every new generation has to use more and more technology, and what was difficult for an earlier generation is not. So to tell you a story, when I went as a postdoc to Oxford and there was a lecture going on and I said, but this something, that professor says, this has an answer, but it involves something called sheaves. I wonder whether I can give you that answer. So I said, yeah, try me. But anyway, so in those days, even when I was a PhD, it was not taken for granted that people knew sheaves, especially a black young man coming to Oxford from that former slave colony. But now all of you people will laugh if anybody even suggests that you guys don't know sheaves. Yeah? Every generation knows more and more. So, and Fulton All Said and Done is now 50-year-old book. Yeah, even more. So you have to look at the internet, look at the latest sources and go read that after this. Very important to be really, armed with all the tools. Your tool bag has to be really, nice. But tool bags are heavy. And there's a lot of investment in learning to even lift it and use it. So one has to finally have a balance. How many tools and then what specific job you are going to. Each one will arrive at your own balance. But don't fall behind. And always remember that your teachers belong to a much earlier generation. 2-3 generations before you as mathematics goes. And so our tool bags are likely to be antiquated and our approach is perhaps has the burden of history, which again, So learn new techniques. So yeah, here's a new technique, meromorphic functions, how to use it. Not really new, but at this level to use it, start doing it. So we set up well divisors of meromorphic functions, which are invertible meromorphic functions on schemes. But then, to show that this works for the solution of pullback of rational equivalence, it's my burden therefore to show that this new kind of well divisor is rationally equivalent to 0 in the old sense. I want to prove this without changing the definition of Chow group, right? So that we proved again doing some algebra that this is indeed so, and that's where we talked about how much this rational function or meromorphic function vanishes on a scheme where, and there was a thickness of that component, and restricted to that it was vanishing. And Sudarshan made yesterday a very pictorial comment. He said, along that thin subvariety it's vanishing somewhat, there's this length or some sense. And then that whole component has a breadth. And there's this, therefore the amount of vanishing taking place is the area, like length times breadth. And that is happening over each one of these components. So you are summing. Yeah, very nice pictorial way of thinking. Okay, so you have to think pictorially, make little analogies, metaphors, things which you know, and connect it to something that you know. So we did all that, and we managed to show that pullback of rational equivalence under flat morphisms of constant relative dimension is again rationally equivalent to 0, and so Chow pullback is done. And it's functorial because it was functorial at the level of cycles. Then we went to pull-push equal to push-pull, and we treated one technical, most important technical case where it was a finite, generically finite morphism, same dimension, by going to the function fields where it was a finite extension of field and an Artin local ring over one and tensor product over other, and then some simple algebra took care of that. And I hope you also read by yourself or figured out how to leverage this into a complete proof of all cases. Any case, it's there in my longer notes. And then we did the open closed right exact sequence. This was a very, very important thing. Okay? And I told you that it is only exact on the right, not exact on the left. Did you give yourself some example where it was not exact on the left? Point in A1, going to 0. A0 of A1 is 0. A0 of point is Z. Yeah? Good. So then I told you about how this is so inconvenient, not knowing the kernel of this. You would ideally like to know. Okay, it's not injective, but then what's the kernel, right? So you want to know what occurs on this side, this side, this side. You know tensor product is only right exact, but what occurs on that side there? Tor1. And that Tor1 map also may not be injective anything. What appears on that side? Another Tor1, and then another Tor1, and then a Tor2, and then so on. And then you are properly armed with homological algebra, armed with all these Tors. If you look at my notes, you will see that, you see, yesterday, who did it for you? I think Amit did it for you. That Cartier divisor D intersected with the cycle of another Cartier divisor E is equal to Cartier divisor E operating on the, yeah, he did that, right? It's done in my notes for the important special case of effective Cartier divisors intersecting properly. And I don't show this is equal to this. I show each one of them is equal to a third thing which is extremely canonical. The third thing is the alternative sum of the lengths of various Tors which are finite length. The one way of doing it, D intersected with the cycle of E, is one way of calculating Tor. And the other one is the other way of calculating Tor. You see, if you want to calculate the Tor of M and N, you can take a projective resolution of M and tensor that resolution with N and take the homology groups of that. Or you can take a resolution of N, tensor with M and take. And the Tor is so-called balanced functor. All these are the same. Okay? So I was trying to understand puzzling over Fulton. Thanks to my being invited to this workshop. As I told you, I am not a specialist of intersection theory in any way. I looked at this with somewhat closely in the past few months because I was supposed to lecture here, and that's why I discovered this new proof of, or not new to the experts it turns out, of flat pullback, okay, by trying to understand Fulton. So I tried to understand that why is this equal to this, and I realized that both sides are the length of a torr. And I had heard that there is something called Sayre's torr formula for intersection. So I took my calculation and then looked up Sayre. Now you can on internet see. And yeah, that was the torr thing. So you can make discoveries yourself. It's not going to win you any credit, but you will get a lot of confidence. Rediscovering mathematics yourself by thinking, hey, what should be this? And let me try this. It's not just that, yeah? So you have to anticipate. For example, in a lecture, a good student anticipates that the next thing is this. But a good mathematician anticipates what may be the next theorem and what may be its proof. So you have to start doing this. So it's there in my notes, this torr calculation and this D, E, E, D. Look in the notes in the chapter 2 and for a neat complete proof. Okay. So this sequence has, just as torr is on the left of the tensor correct exact sequence, there is higher Chow groups to the left of such sequences. And these higher Chow groups are too advanced for this workshop, and you can put it in your reading list for later on. Remember the word higher Chow groups. Who invented the higher Chow groups? Spencer Bloch. Okay? Next week you are going to have a course on the Riemann-Roch theorem, right? Who is going to teach that? Srinivas. What's the connection? Bloch is Srinivas's advisor. Okay? So, and he's an expert on this stuff. So is Anand. So are many of the others. Not me. But for me, they are all experts, remember. So you can ask them more questions about all these higher Chow groups and whatnot later on. But get asking questions, get chatting. You have to chat with these guys. Perhaps I am much older. You might find it easier to more easily talk with people closer to your age. Then you should be doing it. Or perhaps we are all so busy having fun together that you guys watch us from a distance and how do you now go and talk? Okay, but break this ice. Huh? Now we come to today's stuff. So I'll talk of Cartier divisor, their restriction. I'll talk of Noetherian induction. Then we'll talk of affine bundles. Amit has done much more really about these, but I'll do some basic things clearly. And then I'll talk of exterior products. This I was not able to figure out in Fulton. So my one failure in understanding the chapter 1 of Fulton is I have not figured out exterior product. I got stuck at points. So I asked the experts. They also cannot answer. Well, okay, so this is what happens when you are outsider to a subject, because then you are going to read what is written with fresh eyes and puzzle over things, while the experts have learnt it in their childhood and now they are busy in something much more advanced. Anyway, so I am stuck on one of those points. Perhaps it will get settled. So next week Srinivas is here. The one case which I could settle, he did it in a much more elegant, better way. Okay, so next week you should ask him questions about this exterior product also. I'll be there around listening to the lectures, so we'll talk. And then Chow groups of affine and projective spaces. We'll settle the answer instead of just A0 and top AN, all of them. And then all this stuff we'll do, telling you what is the universal property of Chow theory and how it comes about. Okay, so let's go to today's slides. Okay, so as you know by now, but then this was not part of earlier lectures because there Amit only talked about varieties. I'm going to talk about schemes. So I have any locally Noetherian scheme. So on that I have this sheaf of meromorphic functions. Inside that is the sheaf of invertible regular functions. And then the quotient is k star mod O star. This time this is not a constant sheaf or anything. Its cohomology is not going to vanish. Okay. For a variety, this is the constant sheaf corresponding to the field of rational functions. Here there is no such thing. So this quotient is the sheaf of Cartier divisors, and it's a global section is a Cartier divisor. And then I have long exact sequence corresponding to this short exact sequence from h0 of this to h0 of this. So if I begin with a global meromorphic function R, that's a section of this, its image under h0 here to h0 there is called div R, the divisor of R. So that's how every meromorphic function, which is invertible meromorphic function, here we are in K star and O star is going modulo. So that is the Cartier divisor of an invertible meromorphic function. Definition clear? Those are Cartier divisors. And if I come from here, so all these global sections are Cartier divisors, and if it's an image of something from here, it's called a principal Cartier divisor defined by a meromorphic function. Not all Cartier divisors are principal, right? For example, if I have P1 and if I have Cartier divisor 1 point, that's not, see, rational functions Cartier divisor is going to have, its Weil divisor is going to have degree 0. So if I have Cartier divisor whose Weil divisor does not have degree 0, can't be principal. Okay? So this you know already from varieties. And if x is integral, this h1 is 0 because it's a constant sheaf. So the connecting morphism, there will be h1 of this, and next there will be 0. So this map is an isomorphism. This is surjective, this is called Picard group, and you go modulo the image of the earlier one, and so now there is no kernel, so I get this isomorphism. So for integral schemes, the Picard groups have this nice description, this modulo this. But this quotient, this modulo this, is called the Cartier divisor classes. These are the Cartier divisors, and you are going modulo rational equivalence. It's called linear equivalence in the context of Cartier divisors. And so that's called the Cartier divisor classes, CACL. This name I learned by reading Hartshorne. Okay. The set of all closed subschemes whose ideal sheaf is locally principal generated by a single section. To that you can make an element of this, because that single section is well defined up to an multiplication by an invertible regular function, because then they will generate the same ideal. If I have principal ideal generated by some x and there's some unit u in the ring, then x times u and x generate the same principal ideal. So there is always that indeterminacy about the element. That's why you are going modulo the invertible things. So the set of all closed subschemes whose ideal sheaf is locally principal generated by a section of Sx, means every non-zero divisor, is in bijection with the submonoid this one. It's locally generated by an invertible non-zero divisor. So invertible is a meromorphic function. And so this is a sub of this, because this Sx is a sub of K star, and so this sheaf is a sub of this sheaf, and therefore global sections are a sub. At the level of global sections, sub goes to sub. Okay? So those are effective Cartier divisors. And now one can ask whether these two definitions are equivalent. After all, one might define an effective Cartier divisor as a closed subscheme locally defined blah blah. Or one may say that it's a section of this K star mod O star which comes from Sx. And this is the same, okay? Same definition. Now, if I have an algebraic scheme of pure dimension, and if I have a meromorphic function, so this is the Weil divisor, and so there is a homomorphism going from invertible meromorphic functions to n-1 cycles, okay? Where n was that dimension. A general scheme, there is no n. So that's why I said, take something which is equidimensional of dimension n. Then these are the n-1. Okay. So I have this map, but it clearly factors through the Cartier divisors. Because when I am taking the Weil divisor of an invertible meromorphic function, had I multiplied that by an invertible regular function, the order of 0 or pole, etc. won't change at all. It's additive. And an invertible regular function has order of vanishing 0. So multiplying by it doesn't change the order of 0 or pole of something else. So it factors through, and therefore really it is Cartier divisors which have veil divisor. So from invertible monomorphic functions you go to Cartier divisors and then go further is the same as directly going from invertible monomorphic functions to their veil divisors. And so being conscious of this, that I don't need to go through this, I can directly define the veil divisor of a rational function. I introduce this notation square bracket R for these lectures. But in anticipation that it is always going to be like this, factor through this, you will see that Fulton all the time writes it as, so what I write R, he writes as div R. He never uses this notation. So always it is first write div, then write R, looks a bit complicated. So to say myself, space is very important in making slides. Something spills over to next. I realize that I can save space if I get rid of this all the time div. So this notation. So remember, this notation is mine and used in my lectures. And if you are talking with somebody else, take care to explain what you mean. Nothing great. I mean, I can see even without thinking, my colleagues have adopted it in their lectures. Okay, it's very natural. Writing it this instead of this saves. Everybody wants to be saved some amount of writing and space. Okay. All right, but when you go read Fulton, remember it will always appear like this. Okay, so here's the exercise. If D is a closed subscheme, that is an effective Cartier divisor, so corresponds to this. Then on the one hand, there is the fundamental cycle of D. What are its reducible components and with what multiplicities they occur. On the other hand, treating it as a divisor in the sense of being here, it has a veil divisor. These two are the same. Simple exercise in definition. I called it exercise. This equals this. So this closed subscheme is this section here. Then the veil divisor is the fundamental cycle of D. Do this exercise, just definition checking. Now, an invertible monomorphic function on a scheme will restrict to an invertible monomorphic function on each component, where it will be a rational function. Components are irreducible ones. Why? Because this invertible monomorphic function on an open subscheme is a regular function. And regular functions certainly restrict to closed subschemes. And if it is invertible regular function, it will restrict to an invertible regular function. Why? Because under any ring homomorphism, units go to units. Why? Because the equation xy equal to 1 implies fxyx equal to 1. Finally down to equations. So I have this restriction and I take an invertible monomorphic function, I restrict it, and then I can take its divisor. And if I have gone modulo an invertible regular function, the divisors are left unaffected. So this is going to factor through Cartier divisors, this construction, showing that you will be able to restrict a Cartier divisor to the reducible components of a scheme. Okay? Equidimensional scheme of dimension n. You can restrict Cartier divisors also, not just invertible monomorphic functions. And then what is going to be the divisor of that? So the divisor of D is the fundamental cycle of D, and that the answer is going to come out like this. How much this D vanishes in Sudarshan's language in the what vertical, horizontal, one of the two senses, and how much that thing has width in the scheme. Multiply, add, total area. Okay. Same formula, because that formula is, earlier you saw, is right for non-zero divisor functions. It's additive, so it's okay for rational functions. And multiplying by a unit does not change either side of it. And so it goes down through the quotient by O star. And so this formula is okay also for Cartier divisors. Okay. So this was a proof. I just now gave you a proof. Because once you know what are the ideas, you can write the x, y, z, whatever it is in your own words. Okay. So this formula is okay. Otherwise, go read this. Written there in all detail. But better, if you understand what it means, you should be able to quickly write the proof. Finally, it will boil down to non-zero divisors going modulo something on a minimal prime and comparing lengths, and it will rest on your technical understanding of artilocal rings, length, associated primes, minimal primes, all such things under the bonnet. Now we come to the promised Noetherian induction. Again, I have not seen it written in this kind of detail anywhere, and I hope I am right. I request all of you to please watch and tell me if I have written some nonsense. Okay? So, take a partially ordered set, that's called poset. P-O set. Poset. And at this point, I don't have to assume it's non-empty. Take a partially ordered set. Keep in mind one particular partially ordered set, namely the natural numbers 0, 1, 2, 3, etc. That's partially ordered in fact, it's totally ordered. So that's the one you have to keep in mind, because whatever I am going to say is going to generalize that situation. That situation is Peano's induction or Dedekind induction, if you want to be set theoretic, which is stronger by the way. But anyway, so this PO set induction is going to generalize Dedekind's induction from natural numbers to partially ordered sets. So what is the statement? So you remember in that situation there is some property, and you want to know that whether all natural numbers have that property. And this property etc. is like grammar and language, which Dedekind converted into, there is a subset, and whether everything is in that subset, whether that subset is everything. Okay? So I don't want to digress on logic at this point, though I am very strongly tempted, but I won't. And so I resolutely stick to mathematics and say I will define properties by subsets. Okay? So I got a subset. So think of T as a property in your mind. That's a subset of S. What X has that property, meaning is X in T. Does everything have that property, meaning is T equal to S? Does 0 have that property? 0 belongs to A. When something belongs, does the successor also belong? That's the kind of thing, inductive hypothesis. And under it, the theorem of induction of Dedekind says that yes, if these two conditions are satisfied, then S equal to N. So we want the analog of that condition, which will make S, that was T equal to N. So I want analog of condition under which T will be S. So there is this following statement. This CTX says for all y in S, for all natural numbers, whenever the natural number is smaller than n, the property is satisfied by that smaller number. So all numbers smaller than n satisfy a certain property. And when that happens, you are required to prove that n satisfies this property. This is the inductive step. So under the assumption that everything smaller satisfies that property, you prove that n satisfies that. Once you prove this inductive property, this property is going to hold for all natural numbers. Okay? To make your beginning, you might want to say that 0 satisfies it, because it has to be satisfied for everything less, and then there is nothing less than 0, so that would be vacuously true. So you don't want that danger. Okay. So this is Noetherian induction. Let T be a subset of S. Suppose that for all S, we have Ct implies X belong to T. Show that T equal to S. This is the exercise. I should have made a little repair in this and taken care of the situation of the minimum. I am for a moment worried that 0 satisfies the property has to have an analog. Okay, I will myself look at it and repair if need be. Okay? Not now. So you understood what Noetherian induction says. It says this is a Noetherian poset. Okay? Okay, perhaps I don't need it. Let's go through it line by line. So I have this statement CTX, which means anything smaller than X satisfies T. And a poset, I'll say, is Noetherian if every non-empty subset of S has a minimal element. And the exercise I am giving you is, if I have a poset which is Noetherian and T is a subset, and this property is satisfied, then T equal to S. And the proof is exercise, but here's a hint. Suppose it was not so. Hint, assume T is not S. then what is there a certain subset which will have minimum? S minus t. So if that property is not satisfied by all natural numbers, then there is the smallest natural number which doesn't satisfy it, right? And then from this you are going to get a contradiction. That's the idea. Okay. So here the main work to be done in proof of Noetherian induction is to prove the inductive step. So it's the smallest fellow who doesn't satisfy it, which means everything less than it satisfies it. So if you have proved the inductive step because everything less than it satisfies it, that also satisfies it. So you have to prove this inductive step. And that inductive step has taken care of the empty, non-empty problem. I never said anything about empty or non-empty in this. Yeah, Anand, okay? I don't have to say anything about empty, non-empty. In other words, the way I formulated it, I don't have to say a separate sentence that all of it has a smallest thing 0 and 0 has that property. I have not said any analog of that in my formulation. And I think I am right. Okay, so all of you stare at it. This requires no specialized knowledge of mathematics. So see whether I have made a true statement and whether the proof I gave you is right. This is Noetherian induction. Now how are we going to apply it? That we'll see. So we'll first apply it to affine bundles. So here's the statement. I have A1 cross X to X, and this induces a surjection of Chow groups. This is a flat morphism of relative dimension 1. So the shift is by 1. So proof, the result is obvious if X is empty, so assume that X is non-empty. Now the set of all closed subschemes on X is partially ordered by inclusion. And because my schemes are finite type over K, they are Noetherian schemes, so this poset is Noetherian. Okay? I can't keep on going down, 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 or up, up, I forget which way this is going. Ideals, what? Ideals can't keep on going up, so these subschemes can't keep going down. So it will stop. So I think I formulated my statement for every non-empty subset has a minimal element. Good. It directly applies to closed subschemes of a Noetherian scheme. I have to prove this under the assumption that the statement is valid for all closed subschemes. That's the Noetherian hypothesis. That for every closed subscheme of X, the pullback map to the A1 bundle gives a surjection on Chow groups. Assuming that I want to show it for the scheme itself. This proof will be the inductive step. That it was true for all smaller subschemes is the inductive hypothesis. You understand the difference between inductive hypothesis and proving the inductive step. So we have to prove the inductive step. Okay. So for any closed subvariety of dimension m plus 1, we must show that this belongs there because we know what this group is generated by. So everything is there, and then I want to show and what is anything generated by cycles which are cycles of closed subschemes. So those primitive generators have to be there if everything is there. They have to be there up to rational equivalence. Okay. So if I take any here, then this should belong to this. All this is happening here and not in Z. Won't happen in Z. So let Y be the closure of that. This closed subvariety of smaller dimension. And if Y is not equal to X, then by induction this is surjective. And if it is indeed that, okay, alright. So look at this Cartesian square. This is what is happening over Y. So remember what was Y. Y was the image of, where is it written? Y is the closure of the image of that closed subvariety. This map is not proper. So if I just took the image, it's not closed automatically. I have to take the closure. So this diagram, horizontal arrows are proper, vertical are flat. So this is the push-pull situation. And therefore I have these equations. This is this, which is V. So now, why could I say this? Because Y was something proper. and so by smaller. So by Noetherian hypothesis, I knew that it is true on Y. So by push-pull, I got it for this particular element. But what if the image of Y was X itself? Then what do I do? So then, if I take, that tells me what V has to be. Because V is one dimension more, and its image closure is all of this. So what can V be? Its inverse image is already one dimension more, and that's of the same dimension sitting inside and closed. So V had to be all of it, right? So in that case, it is simply the inverse image of the fundamental cycle of the base, because its inverse image is all of it. So now you have to think the remaining situation. Dimension is m plus 1, and V defines a close point in that fiber, therefore. And we want to get that, okay? But such a thing, if it was only a point and A1, and I have got some close point up there, and I want to show that it's coming, okay, from somewhere below, what will I do? Where is it coming from? But actually such a point is going to be rational equivalent to 0. There's going to be a rational function which is going to define it. So I use the existence of this function over the generic point, which extends to a function on that open set, some open set. Complement is a proper closed subset for which the Noetherian hypothesis holds, and all of it I can put together in that diagram which Amit wrote yesterday, the exact sequence below, exact sequence above, and the maps, and diagram chasing. So that is how the proof goes. This is the diagram. So the proof is very simple. The philosophy is very simple. You have to go through this step by step yourself through all these 4 slides. Read. My reading it with you just now is not going to be helpful. You have to read it at your own pace. Go back 2 lines, read that, turn page, come back. Close reading of 2 slides is what you have to do. At the end of it, you understand this proof, or you come to me saying, hey, this line doesn't look right. I'll say, oh, let me read. Yeah, you're right, indeed. There's a misprint. This should have been this. Or I say, no, it's perfectly all right. Go back and try again, and I'm not going to tell you. Because this is right, and your doubt has a simple answer, which I'll leave to you. So I'm not going to spoon feed this proof to you, but I'll entertain your questions, because after all, you might have some comment, I might have made a mistake, or your question may be something like, why you are working so hard? I have a simpler argument here. Perfectly possible. That's why I'll listen to what you have to say, in the hope that I'll learn something or I'll get a mistake corrected. But I'll not spoon feed the answer to you. Got it? Don't come and say, help me understand this. So at the beginning of one of the first year lectures, I said, you are all welcome to ask difficulties. Difficulties are of the following 2 kinds. 1, what you are saying there is wrong. I am willing to entertain that. Second kind of difficulty. Oh, I have better theorem or I have better proof. I'll listen to you. But if you come to me saying, I don't understand it, can I explain it to you again? I'll say, how many nights did you lie awake tossing and turning in your bed before you have come to me? So go back, go back. You're going to be a mathematician. So you have to have that self-reliance and that pride that I can fix it. How can I not? If you can do it, I certainly can. Okay, this is what in your mind you should be saying about your teachers. You know, hey, this fellow also understood this. So I will certainly say it in your mind, please. Shouldn't say it openly. That's regarded rude. Say it in your mind. Extremely important. Okay. All right. So you're going to go through those last 3 lines and come back. And I'm not going to waste writing them on the board and whatnot. I have written them here and written in the notes twice. So once I have this, Simple arguments, simple steps at every. By the way, Hartshorne has something like this also, but he works for varieties. He has a much better situation, and perhaps he proves isomorphism of some kind. Anyway, all right. So look at Hartshorne if you want, but look at this. So if it's an AN bundle, you can factorize it. First project along the last coordinate, then last one. Successively you get a large number of A1 bundles. Each one of them, the pullback is surjective at Chow groups. Therefore, overall pullback is surjective. And then once I have it for AM, again this kind of diagram gives it for anything by Noetherian induction. Because there is an open set on which it's a trivial AM bundle. There it's an SO, there it's surjective. Complement is a proper closed subscheme. There it's an isomorphism by Noetherian inductive hypothesis. And therefore by a diagram chase, here you will get it as surjective. Okay, this is how we are going to use Noetherian induction in all this. So here's a statement of Noetherian induction. Do the exercise, write it down, and then come back and see how it is deployed here. And then spot all those places where you have been using Noetherian induction all the time, because algebraic geometry textbooks all the time routinely say that now by Noetherian induction. I used to think that by that they meant that, you know, it is true in this dimension, I want to prove it in this dimension. Let me assume it is true in smaller dimension. But the complement of this U is a proper closed subscheme. It's not necessarily of lower dimension. Then I thought perhaps they meant some kind of a double induction over dimension and the number of irreducible components, and you do a 2-index induction. No, you just do a one-shot induction like this. Okay, so that was the thing about affine bundles. This exterior product I am not going to elaborate. I have called it exercise. I called it exercise at a point of time where I thought I have proof. But my proof only works under the assumption that the field is perfect. I asked the question to Srinivas, he has a better proof. The better proof also works under that same hypothesis. And so we don't know right now how to figure it out when the field is not perfect. Fulton is mum about it. I mean, he pretends as if there's no problem at all, and he just goes through it, hardly making a comment. No? Fada, left, right. So maybe he knows and he has not written. After all, he is in a hurry to get to interesting stuff. Maybe by now Srinivas has figured out how to make his proof work even without the restrictive hypothesis. My proof, I have been struggling. I can't seem to push it beyond a certain point. Anyway, so this is exercise to you under the hope that what we couldn't do, you will do. And that's how mathematics has advanced all these thousands of years, because each next generation did what their predecessors could not do, you see. So this is absolutely routine, and you have to back yourself up saying, oh good, that's interesting, you guys couldn't do it, huh? Okay. But after that means several sleepless nights. You should be willing to put in all that, you know. There's a pain barrier, you have to torture yourself, pain. This is very apparent to you with athletes. How they have to break the pain barrier to really punish yourself basically. You have to be able to put through punishing amount of hard work, be obsessed. It's not a normal life. A research mathematician is not a normal life. A normal, well-balanced life, you know, it's like this, that, well, this joke is completely different, but I'll tell it. A little boy goes to his mother and says, Mother, I love mathematics. Can I become a mathematician when I grow up? So the mother says, no. Why not? No, that's impossible. Why impossible? You know, son, either you can grow up or you can become a mathematician. Okay, all right. So, anyway, so this, you know, your eyes should light up that, oh, our teachers have not been able to fix it so far. Here's my chance. You know, all the time you have to look for things where you can do better. You have to believe yourself that you can do better. And after all, you have had a much better education, much better grounding at a much earlier age than your teachers did. Okay? And so if you are not able to go further, that will be a pity. So here's your chance. Little chances everywhere. Oh, this is not known. Okay, mental note. Now you are at an age where you should be looking for difficult research problems. Okay? Alright, so I cannot do this exercise, and my proof of associativity is based on this exercise. And for Fulton, associativity, just writes. Okay. So now let's come to Chow groups of affine and projective spaces. So An and Pn are varieties of dimension n, and therefore the top Chow group is Z. Okay, this induces a surjection. This is a flat morphism of relative dimension n. So it induces a surjection of Chow groups in the reverse direction. That is a theorem about affine bundles. Simplest affine bundle is the affine space, which is affine bundle over spec K. Therefore, the Chow map is surjective. And you know, for the point, there is only 0th Chow group, and it's going to the top one there isomorphically. All other Chow groups here are 0, therefore all other Chow groups there are 0. Finish. Okay? So, therefore that space has no other Chow groups than the top one. Notice how funny this is. This is behaving like Borel-Moore homology and not like singular homology. See, in singular homology, it will be the 0th group which will be Z and all others will be 0 for the affine space. For Rn, what is the singular homology of Rn? The 0th homology is Z, everything else is 0. But if I took the, let's say, compactly supported cohomology, then the answer will be like this. Top will be Z and others will be 0. Okay? So this is like Borel-Moore homology. The cycle, the top cycle is not the boundary of anything. Lower dimensional cycles are boundaries. But that top cycle is not compact. So singular homology cannot have that top cycle. Singular homology, the cycle is supported in a compact. It's a finite sum of singular simplices. Each one of them has a compact image. Okay? While our basic cycles with which we defined Chow homology were not compact. So this is not like singular homology, but like Borel-Moore homology. Okay, now for projective space. This is more fun. So if I have projective space, every closed variety of dimension n-1 is defined by the vanishing of irreducible homogeneous polynomial. This is Archon chapter 1. Yeah? All of you know this. And degree, that's the degree of that hypersurface. That defines an isomorphism. Because if something is defined of degree d, it's by homogeneous polynomial of degree d, divide by dth power of a linear polynomial, one of the variables. Then that's a rational function. It's a homogeneous, same degree, degree 0. So it's a rational function whose divisor is that hypersurface of degree d minus d times a hyperplane. So anything is d times the hyperplane. Is d times the hyperplane itself rational equivalent to 0? No, no chance. Okay. So all this is done because degree is a well-defined map going to Z, and that is what gives you this isomorphism. An-1 Pn is the infinite cyclic group defined on a linear subspace of dimension 1 less. Linear projective. The linear means this is projective linear, not vector linear subspace. Linear meaning it's defined by what? Linear equations in the projective space. Degree 1. Now how about the other ones, lower ones? So you consider a whole filtration by linear subspaces, each one defined by vanishing of more and more coordinates. Okay? So this is defined by the vanishing of one coordinate, this is by two coordinates, this is by all but one coordinate, and that non-vanishing coordinate you can call 1. So it is 1, 0, 0, 0, 0, or maybe that one is in the last, I don't know. So that's L0, then there's L1, there's L2, and each is sitting like a hyperplane in the next. So you have got this whole filtration of the projective space. They have their fundamental cycles, the square bracket Li. Those are the generators for the Chow group. This is the result. This is the result proved here. How do you prove it? The idea is, if I have anything else, I need a certain candidate, which is one of these Li's, and I need to be able to compare it. And I need to leverage my knowledge of lower dimensional projective spaces. Does a higher dimensional projective space have a map to a lower dimensional projective space? Except constant maps. Okay. See, in affine spaces, what we did, we regarded AN as an A1 fibration over AN minus 1, AN minus 1 as an A1 fibration over next. And we just leveraged this, bootstrapped this step by step. So A1 bundle is all that we wanted and went on applying it again. Think of that strategy. When I talked of P1, first thing you should have noticed is, what was the strategy for AN? Can I apply it for PN? So you cannot directly apply that strategy. But there is a little trick. If I have indeed a cycle, and that cycle is not everything, then there is something left. And from there I can project. If I take P2 and I remove a point, the rest of it has a projection to P1. And what's the fiber of that projection? A1. Okay? It's actually a bundle. It has a zero section. Yeah? So the situation, you can try to have that old proof if you are able to project from somewhere. Now if I have cycle, suppose I am on an algebraically closed field, then it's not going to fill up everything. There's going to be something left from which you can project. To what do you want to project? So, if there's the dimensions from where you are going to project. You see, there is not just, in P2 there is projection from a point of the complement of that point on P1. In P3 you can think of two different kinds of projections. One would be remove a point of P3 and from that point project P3 onto P2. Other projection is remove a line and from that line you project rest of it to a line. Okay? So if you want to understand one cycles, you might like to project them to a P1 because then that will be a nice finite projection where you understand things. So how much you can project? You want to project as well as possible to something as small as possible, then you will get a good theorem. So how to project? To find a linear space which doesn't meet it. So if the dimensions add to one less, so if there is a curve in P3, there is a P1 in P3 which doesn't meet the curve. True? But this happens if your field is algebraically closed. If your field is a finite field, there simply may not be enough points. That earlier thing, though small dimensional, may fill up everything. It's like Suprabhat's example of what may go wrong in A0. Yeah? There was no line left. So how did we tackle it? We went to an extension field. And that led to a proper morphism. So if need be, we can do this projection by going to an extension field and then taking up proper morphism from there. So I have cryptically said it here. If our base field K is finite, we may have to base change to a finite extent to obtain such a basis for projection. Do it in some extension and there take proper push forward. But when you do all this, you are going to use the proper push forward theorem always. Because I have this subscheme of a certain dimension M and I am projecting it from a linear subspace of dimension M prime, so that M plus M prime is less than n of that Pn. Then this projection from the closed subscheme to the projective space of that complementary dimension is a proper morphism and I can apply proper push forward theorems. And so doing this in that lower dimensional space, this projection, so by induction, I assume I have proved it for a lower dimensional projective space and so on. And I also assume that I have proved it for a n minus 1 of Pn, right? So if I can make it as a hyper surface in a lower dimensional projective space, I can apply induction. This is the strategy. Have you understood strategy? My telling you the strategy rapidly doesn't mean it sinks in completely. You have to think about it. But my going through the proof line by line is, in my opinion, useless. Because that doesn't, you follow it line by line and then later on it's gone. And for you to follow line by line, I have to needlessly spend a lot of time. Because anyway, it's all going to go away. So later on, when you understand the strategy, you need to carry it out yourself. You are struggling to carry it out yourself. At that point, it helps line by line. So, here what was said. So at that point, you consult this. Okay? So this is a very unusual strategy I am following, because usually, to my great unhappiness, mathematics lectures, most of them go and do a textbook style line by line account of the material. Then why do I need to go to lecture? Only if there is no textbook. That's why I enrolled myself in MSc Mathematics while I was a physics student, because I didn't like the lab. And I used to go and write the exams, but the university being what it is, I was thrown out for attendance exactly equal to 0. So something had to be done. The physics HOD became Vice Chancellor, luckily at that moment, and he condoned me. So I passed my MSc Mathematics by not attending lectures. Therefore, I absolutely hate this idea of line by line looking at the board. And luckily, I got a job for myself where I didn't have to teach either. So all my life, I have not taught undergraduate or MSc. I have only taught either summer school kind of thing for bright kids or more advanced courses, and where I happily not implemented, or where I happily implemented the style of explaining the points and not writing line by line. Okay? Alright, so no reason to change that now. Alright, so that is the proof for the projective case, that by dimensional reduction through an appropriate projection, that cycle, whatever it is, you project it as a cycle of codimension 1 in a smaller dimensional projective space. And cycles of codimension 1 in a projective space is the case that we dealt with earlier using degree, and which is dealt with in Hartshorne chapter 1. So you are through, and that answer is Z. So every answer is Z. So that is why all groups are Z, and that answer comes in terms of an appropriate linear hypersurface in a projective space, which in terms of your ambient space is this whole sequence of one extra dimensional linear spaces. So those are exactly the generators of this. Okay? So that is the Chow group for this reason. Dimensional reduction all the time through projections, all the time making the cycle of interest into a codimension 1 cycle in the appropriate dimensional linear subspace. For these projections, you need a linear subspace which doesn't intersect it. If your field is algebraically closed, you have it straight away. Otherwise, go to a further finite extension and use proper push forward. Okay? Alright, so now I have 15 minutes left, and I am going to explain why rational equivalence in doing Chow groups. So you know that the function field of P1, so my P1 is proch KST, is equal to polynomials in this ratio. This ratio is really the affine coordinate on the complement of infinity. Okay? And so its divisor, this vanishes at 0 and has pole at infinity. Now if I have a variety of dimension D over K, okay? If R is algebraic over K, then this class is 0, right? If R is algebraic over K, then you already know it's a nowhere vanishing, it's a non-zero rational function. So it's a non-zero constant in a field extension. It has no zeros. So its divisor is 0. See? After all, I is a rational function on something. And then, well, what is it? Where does it vanish? I don't know. So spec C, so suppose my base field was R, K equal to R. Then spec C, is it a finite type K algebra? Sorry, is C a finite type K algebra? Yes. So is this a variety? Yes. Integral domain, finite type over K. Spec is a variety. What is the dimension of this variety? 0. Is I a rational function on this? Yes, it's a regular function. What is its divisor? I doesn't vanish anywhere. No 0, no pole. So if something was going to be algebraic over your base field and non-zero, it has no 0, no pole. So its divisor is 0. But suppose that it was not algebraic over. Okay? So then it defines on a large open set a morphism to A1. which is flat. See, Fulton is mum about this. I am pointing out to you that a rational function, even on that open set where it is regular, may not define a flat morphism to A1 because it may be algebraic. But if it is not algebraic, it will define a dominant flat morphism to A1. You know, you might be used to thinking that a regular function is a morphism to A1. That's what it is, right? Regular function is a morphism to A1, right? So, a C-infinity function on the manifold is a map from the manifold to R. Similarly, a regular function on any scheme, take an abstract scheme X. A regular function on that scheme X is nothing but a morphism from X to A1Z, right? Because, okay, what's an element of a ring? An element of a ring is a ring homomorphism from ZT into that ring. An element of that ring is a regular function on spec of that ring. And such a homomorphism is a morphism from spec of that to spec of ZT. Spec of ZT is A1 over Z. For a general scheme, I said Z. If all your schemes are going over K, then I would have said KT. And therefore, a regular function on any scheme over K is nothing but a morphism to the line over K. Yeah? You knew this? When one talked of regular functions, where you saying, oh, this function to the line, here's a map, that's a regular function. Same as in differential geometry. Yeah? Now that function, if that regular function corresponds to a ring element, what was algebraic over base K, then that function is not going to be surjective or dominant. If it is transcendental, then it's going to be dominant. Transcendental, and if it is not transcendental, it has no chance of being flat. If it is transcendental, it will be flat if your scheme is, say, integral. Because flat over A1 means flat over KT. When is a module flat over KT? Torsion free, right? And so if something is a domain, it has no torsion. It's torsion free. So then it will be a flat. So you see, Fulton without any comment will start saying that here's a non-zero rational function. It's defining a flat morphism to A1 or a big thing. However, it doesn't define a morphism to P1. Why? If it's a curve, regular curve, it defines a morphism to P1. Because at the missing points, by evaluative criterion of properness, you can go to P1. From A1 is sitting inside P1. A regular function, therefore, is a morphism to P1 on that nice open set where it is defined. Now look at the bad set. It may have some divisor left still in it. Look at its generic point. There it's one-dimensional. Suppose it was a DVR. Then by evaluation criterion, you can extend it there. Suppose it was a curve, a regular curve. Then that's all the problem. At some points, it's not defined. But then you can extend it there. Huh? Got it? The Riemann removable singularity theorem. Suppose I have a curve and if I make some, or if I take a disk, punctured disk. Suppose from the punctured disk, I have meromorphic function to Pn. Then I can extend it to a regular function to all of the punctured disk. How? To give a meromorphic function to Pn, I have to give the coordinate functions. So now because it's a function to Pn, I look at the coordinate functions. If all of them are regular and at least one of them is non-vanishing, then it extends to a morphism to P1, because to give a point of P1, I have to give a tuple in which not all of them are 0. But what if all of them have poles? Then I look at the worst pole and multiply everything by that power of Z. Map into Pn doesn't change. Now one of them is going to be at least non-vanishing and the others are going to be regular, and so there's a limit at Z equal to 0. And that limit is how I fill the missing point. This in algebraic geometry is called valuative criterion for properness. Valuative criterion for properness. That disk with a puncture is called valuation ring or discrete valuation ring or something. And this method that put in a multiplier and cancel all the poles, it does not affect the map to the projective space because the same function on all factors. Okay? This is called Pn is proper over the base. So this is a very ancient technique which you always know, comes in a new package called valuative criterion of properness. It is explained in a book called Hartshorne, who does not bother to tell you that this is exactly what is happening. Okay? It's as if as if complex analysis doesn't exist, as if topology doesn't exist, and somewhere in appendix something little bit. This is not right in my opinion, and that makes very weird, lopsided, compartmentalized. Anyway, so you see it's very simple, this validative criterion for properness. So this works in a one-dimensional situation, because that 0 where it is badly defined is defined by one equation. What if it had greater codimension? What if it was not locally principal? Then you won't be able to use this. Okay? And so you won't be able to extend a regular function to a map to P1. Then what do? Then some kind of blowing up, some kind of construction allows you to extend it as a regular function to P1, not from your original space, but from some kind of a covering. Covering which is not finite sheeted, something which may have positive dimensional fiber. Then you can define it up there. So I wish to show it to you with a simple example. So this is some simple trivial things which I asked you to prove. Let's go on to an example of this. Here's the example. Suppose I take A2, a fine plane. I take the rational function y upon x. Where is it defined? As a regular function. This is y equal to 0. This is x equal to 0. So y upon x is defined on the complement of this. This is the bad locus. Because this is where x is 0. Elsewhere it is defined as a regular function. Is it defined to P1? So to be able to define it to P1, okay, y upon x, if there was if this ratio y upon x had some kind of a limit at the bad points, then I'll say, even if the limit was infinity, I'll say send it to the point at infinity on P1. So I need to be able to take a limit as I go to the points where it is not defined. So you might have a regular function, regard it as a morphism to A1. It's not defined at some point because perhaps it's infinite there. Okay, go to there. If it limit is infinite, send it to the infinite point of P1 and the function is extended to the missing point. Problem is, if I approach this along different lines, this y upon x takes different values here. So I cannot extend it to this point. Solution, replace this point by a whole lot of other points, 1 point each for the slope. So for each line going through that, a different point. That you know is going up. So blowing up can make the indeterminacy go away and your morphism now becomes a morphism to P1. So that is the idea by which you can have a new variety over the old variety, and leaving out this, elsewhere I have not changed the variety. And rest of the points here I will happily send to infinity. It is here that I get this problem of different ratios of numerator and denominator. If I go to any other point, the limit is going to be plain infinity. Send it to infinity. Okay? So from this new space, I have morphism to P1. Now the divisor of the original one is the push forward of the divisor of this new morphism to P1, where I declare the divisor of a morphism to P1 as the fundamental cycle of the inverse image of 0 minus fundamental cycle of the inverse image at infinity. So this way, I can represent divisors of rational functions on my starting variety in terms of push forward of some special kind of divisors, pullback of infinity and pullback of 0 on some other space. That other space is birational with this one, and that rational function is the same as this rational function therefore. So this is a new way of representing divisors of rational functions as pullbacks of the cycle 0 minus infinity from P1, but not by a morphism from the original space, but by a morphism from generically finite covering, where that morphism is defined. Otherwise, the morphism is not defined down there. So you go there, but it doesn't change the rational functions. Okay? Therefore, you get the Weyl divisor of the rational function that you are interested in by this construction. Got it? This is the idea of representing rationally equivalent to 0 via morphisms to P1. And with this, the last two slides, universal property of the Chow theory. So suppose somebody set up some other homology theory with the same cycles. Remember, my question to you is, why go modulo rational equivalence? Cycles are justified. That's the geometric meaning of what we are doing. So what should I go modulo? Okay. So one of the things, let us agree, is you agree that the point at 0 and the point at infinity should define equivalent cycles on P1. You already know your theory of curves, you already know your importance of linear equivalence, whatever, and you know these two, I want to be equivalent. In singular homology, would have told you the same thing, that this point and that point, and this is compact, so singular homology works very well. This and that should define the same homology class, this point and that. So any two k-rational points, 0 and infinity, after all your field might be F2, in which case there are only 3 k-rational. So you declare any two of them, concreteness sake, 0 and infinity, to be equivalent. Otherwise, I have the push forward on cycles, I have the pull back with respect to flat constant relative dimension, push forward with respect to proper, and I want an equivalence, and I want this much from the equivalence, that the point at infinity, point at 0 on P1 are the same. This forces exactly rational equivalence on you. Why? Because the rationally equivalent to 0 Weyl divisor of a rational function is exactly produced by a pullback, flat pullback, and a push forward from 0 minus infinity. Why was that pullback flat? Because I am doing it by a non-constant rational function. Non-constant rational function, not constant in sense, not even being algebraic over the base field. A transcendental rational function produces a flat morphism. It's dominant, but therefore it is flat because that's one-dimensional, regular, and so torsion-free is what it means. Okay? And so I have the alternative description of rational equivalence as pullback of 0 minus infinity and push forward. And that I want to kill, so I am killing all rational equivalence. So any other theory can only say, let us kill some more things. But this much is forced on you. And therefore, if you are only going to kill rational equivalence, the resulting homology theory is universal, because anything else you are going to kill more, so everything else is a factor of this. Okay? So this is the universal property of Chow homology. So here it is said in so many words. Suppose I have a functor from the groupoid of schemes. Groupoid schemes meaning it should at least be functorial with respect to isomorphisms, otherwise you are not bothered. To Z-graded algebras, functorial, together with the functorial surjection, which means your cycles are of your theory are generated by the algebraic cycles, closed subschemes. And suppose there is a functorial push forward and pull back, which is the usual one on cycles. And finally, suppose that 0 and infinity on P1, these cycles define the same cohomology class in your theory B0P. In that situation, for any transcendental R and V a closed subvariety, then we have constructed a morphism from a certain birational covering of V to here, such that the divisor D has the alternative description, pull back by this flat morphism to P1 corresponding to the transcendental T, and push forward with respect to the proper morphism. And that is how the Weyl divisor looks. If this is 0, then this is 0, therefore this is 0, therefore this is 0. So it follows that R has to go to 0 here. And if R was algebraic, then already it's physically 0. The Weyl divisor is physically 0. No need to kill it further. And so everything rationally equivalent to 0 in our old sense goes to 0 in this new hypothetical new homology theory. So the new homology theory is the quotient of this. And so this A, F lower star, F upper star is universal among all homology theories on algebraic cycles, will satisfy those three requirements which we listed here. It's a functor of this kind, and the pullback and the push forward and the normalization with respect to these 2 points. Okay? Alright, that's it. Thank you. It was fun talking with you. This is the end of my course.